Good afternoon, everyone. My topic is under the subgroups, and this is the continuation of report of Saludo and Bolisar. So, Theorem 4.1.13. Let H and K be subgroups of a group G, then HK is a subgroup of G if and only if HK is equal to KH. So we have proof here. Suppose each key is a subgroup of G. Let small kh is element to kh, big kh, where it small h element to big H and small key element to key. Now, h is equal to he element to h key and key equal to e key element to h key. Since each key is a subgroup, it follows that small kh element to h key. Hence, kh is a subset of h key. On the other hand, let h key is equal element to h key. Then, h key inverse element to each key and so on. Each key inverse is equal to each sub 1 key sub 1 for some each sub 1 element to h and key sub 1 element to key. Thus, h key is equal to each sub 1 key sub 1 inverse is equal to key sub 1 inverse each sub 1 element to key h. This implies that each key is subset of kh. Hence, h key is equal to kh. So, ato siyang prove nga ang h key is equal to kh. Conversely, suppose h key equal to kh. Let h sub 1 key sub 1 h sub 2 key sub 2 element to h key. Now, key sub 2 inverse each sub 2 inverse element to key h is equal to h key. This implies that key sub 2 inverse each sub 2 inverse is equal to h sub 3 key sub 3 for some h sub 3 element to h and key sub 3 element to key. Similarly, key sub 1 h sub 3 equal to h sub 4 key sub 4 for some h sub 4 element to h and key sub 4 element to key. Thus, h sub 1 key sub 1 times h sub 2 key sub 2 inverse is equal to h sub 1 key sub 1 key sub 2 inverse and h sub 2 inverse h sub 1 key sub 1 h sub 3 key sub 3 is equal to h sub 1 h sub 4 key sub 4 h key sub 3 element to h key. Hence, each key is a subgroup of G by theorem 4.1.3. So, corollary 4.1.14. If H and K are subgroups of a commutative group G, then H key is a subgroup of G. So, we have proof here. So, since G is a commutative, H key is equal to KH. That is the commutative property. The result now follows by theorem 4.1.13. So, dito sa theorem 4.1.13, na nag-proof ta dito nga si HK is equal to KH and that is a commutative property. The following theorem gives another necessary and sufficient condition for a product of subgroups to be a subgroup. Theorem 4.1.15. Let H and K be subgroups of a group G. Then HK is a subgroup of G if and only if HK is equal to subgroup generated by H union K. So, we have proof here. So, ato i-proof diri nga, then atong ikuan nga si let H and K be subgroup of a group G. Then HK is a subgroup of G if and only if CH key is equal to subgroup generated by H union key. So we have proof here. First, suppose that H key is a subgroup of G. Let small h element to big H. Then H is equal to HA element to H key. Thus, H is a subset of H key. Similarly, key subset of H key. Hence, H union key is a subset of H key. Since subgroup generated by H union key is the smallest subgroup of G containing H union key, it follows that subgroup generated by H union key subset of H key. Let H key small h key element to big H key, where it small h element to big H and small key is element to big key. Hence, since H is a subset of subgroup generated by H union key and key is a subset of subgroup generated by H union key, we have H and key element to subgroup generated by H union key. Thus, H key is an element of the subgroup generated by H union key. This implies that H key is a subset of the subgroup generated by H union key. Hence, H key is equal to subgroup generated by H union key. The converse is immediate since H, the subgroup generated by H union key is a subgroup and H key is equal to subgroup generated by H union key. So let B a group. Let G be a group. We denote that the set of all subgroup of G. The set of all Theorem 4.1.16. Let G be a group. Then the set of all subgroup of G and less than or equal is a lattice, where less than or equal is set inclusion relation. So we have proof here. Proceeding as in example 1.4.5, we can show that the set inclusion relation is a partial order of the set of all subgroup of G. We now show that for all A and B element to the set of all subgroup of G, A and B, A or B element to the set of all subgroup of G. Let A and B element to the set of all subgroup of G by theorem 4.1.6. A union B or A intersection B element to the set of all subgroup of G, and by the definition of the set of all subgroup of G is the subgroup generated by A union B element to the set of all subgroup of G. Now, A and B is a subset of the subgroup generated by A union B, and so subgroup generated by A union B is the upper bound of A and B. Let C element to the set of all subgroup G of G be such that A subset C and B subset to C. Then A union B subset to C, and so the subgroup generated by A union B is a subset of C. Thus, the subgroup generated by A union B is the last upper bound of A and B, that is, A and B is equal to the subgroup generated by A union B. Hence, A and B is element to the set of all subgroup of G. Next, we show that A or B is equal to A intersection of B, that is, A intersection of B is the greatest lower of A and B. Now, A intersection of B is a subset of A, and A intersection of B is a subset of B. And so, A intersection of B is the lower bound of A and B. Let D is element to the set of all subgroup of G, and D is a subset of A, and D is a subset of B. Then D is a subset of A intersection of B, and so A intersection of B is the greatest lower bound of A and B. That is, A or B is equal to A intersection of B. Therefore, A or B is element to is the set of all subgroup of G. Consequently, is the set of all subgroup of G in the and less than or equal to is a lattice. So, lattice daw na siya. The lattice, the set of all subgroup of G is, and the less than or equal in theorem 4.1.16 is called the subgroup lattice of the subgroup G. So, ang tawag ana niya kay the subgroup lattice of the subgroup G. Let T, big T is a less than or equal be a sublattice of the set of all integers of G, and less than or equal, that is T sa subset of is the set of all integers of all subgroup of G, and T is less than or equal is a lattice. The poset diagram of T and less than or equal is called the lattice diagram. The lattice diagram will be useful in studying the interrelation among the subgroups of a group. Consider the following example. So, we have example here. So, example 4.1.17. So, ang 1. Let G is equal to the set of 1, negative 1, I, negative I. Then G and star is a group, where star is the usual multiplication of complex number. So let S is equal to the set of 1 and the set of 1 and negative 1 and G. The lattice diagram of S is, so mao ni the lattice diagram niya, si G na sumpay siya ni sa kuan 1 and negative 1 and negative 1 and negative 1 nasumpay siya sa 1. So number 2, let G is equal to the set of order paired 1 and 1 and order paired 1 and negative 1, negative 1 and 1, negative 1 and negative 1. Then G star is a group where star is defined by A and B star C and D is equal to C D B D for all A and B, C and D element to G, where the multiplication A, C, and B, D take place in the integers. Let E is equal to the set of order paired 1 and 1. Let H sub 1 is equal to the set of 1 and 1 and 1 and negative 1. H sub 2, the set of order paired 1 and 1 and negative 1 and 1. And H sub 3, order paired of 1 and 1 and negative 1 and negative 1. So let H the set of E, H sub 1, H sub 2, H sub 3, G. The lattice diagram of S is, so mao ni siya lattice diagram. So ang G naa siya gikuan nga kuan niya part niya kay h sub 1, h sub 2 and h sub 3 and nagkuan siya sa A. So we say from this example that a lattice diagram gives a visual picture of how subgroups of a given group are related. Next, we consider an example of a group generated by two elements. We list several properties of the group. We ask the reader to verify these properties. We will study these types of group in more detail in later chapter. So, example 4.1.18. Let G is equal to the subgroup generated by A and B, where A raised to the power of 3 is equal to A, B raised to the power of 2 is equal to A, and A B raised to the power of 2 is equal to A. Then, so 1, A B is equal to B A inverse, B A is equal to A inverse B, and A squared B is equal to B A. 2, G is not commutative since AB is not equal to BA. So, there is a 1, di ba? Ang AB o BE, dili sila equal. So, G is not a commutative since AB is not equal to BA. So, number 3, BA raised to the power of S is equal to S raised to the power of A inverse B for all positive integers S. So, number 4, by 1 and 3, so, A raised to the power of R, B raised to the power of T, A raised to the power of S, B raised to the power of G, where A raised to the power of R plus S, B raised to the power of G, if I is equal to 0. So, ang equation po natong gamiton nga, A raised to the power of R minus S, B, I plus raised to the power of I plus G if ang I is equal to 1. Mao ang kuan niya dira. Ang given. So, since A raised to the power of 3 is equal to A is equal to B squared. Every element of G is of the form A raised to the power of R, B raised to the power of I, where R is greater than or equal to 0 and less than of 3 to 3. So, I is equal to 0 and 1 by 4. So, dito sa 4, di ba, nakaingon to nga, ang I is equal to 0 and ang I is equal to 1. So, number 6, G is equal to the set of A, B, A raised to the power of 2, and A raised to the power of 2B. Thus, the cardinality of G is equal to 6. So, nasa'y cardinality of 6. So, ato siyang maihap 1, 2, 3, 4, 5, 6. Dayon, number 7, order of an element of A is equal to 3 is equal to order of element of A squared, and order of an element of B is equal to order of an element of AB is equal to order of an element of A squared B is equal to 2. Is equal to 2. Then number 8, the only subgroup of G are E, the set of E, and the subgroup generated by A is equal to subgroup generated by A squared. B is the subgroup generated by B, the subgroup generated by AB, and the subgroup generated by A squared B, and G. So, G is called a dihedral group of degree 3 and is denoted by D sub 3. In general, a dihedral group 1 raised to the power of 1 of degree n is D sub n is equal to the subgroup generated by A and B, where A B squared is equal to E, and order of an element of A is equal to n, and order of element of B is equal to 2. In Chapter 5, we consider a dihedral group of degree 4.4 D sub 4 and study this group in details. And thank you for listening. And that's all my topic. Thank you.